Regression is one of the most widely used techniques in machine learning. Within the machine learning process, our regression model fits into the model building and model evaluation phase. The goal of regression is to assess the relationship between one or more input variables and a continuous output variable, and we can summarize that relationship with a line of best fit. The line of best fit allows us to make predictions about the value of a target variable in a given scenario. So here we can see we have an ad spend of $27,000. Our previous observations give us a line of best fit, and we can make a prediction as to what sales we're likely to get from that ad spend. Not all scenarios are so simple though. Sometimes relationships can be linear, like that first example that we saw. But in other scenarios, relationships are more complex. Here we've got an example of a non-linear relationship between the amount of water and the crop yield we get from a farm. Before we go any further, I just want to clarify the various pieces of terminology used within regression. So when we talk about model inputs, there are various terms that might be used. In general, these are predictive variables, and we might call them inputs, independent variables, explanatory variables, or we might just refer to them by x or x1, 2, 3 if there's more than one. On the other side, our target variable can also be known as an output, a dependent variable, a response variable, or simply just referred to as y. But in summary, the goal of regression is to understand how those predictive variables can help us predict the target variable. Simple linear regression is the simplest form of regression analysis. So we have one input variable x and the target variable y. And as with any straight line, we can give it an equation in the form of y equals mx plus c. Y is the target variable we're trying to predict. X is the input variable. M is the coefficient value or slope, which means it's the amount by which y changes for every change in x. It tells us how steep the line is. And finally, the line doesn't always go through the origin, so c represents the intercept. It's sometimes helpful to think of the intercept as what would the likely value of y be if x were 0? But that doesn't always hold true, so be careful with that one. More generally, it just represents that intersection point on the y-axis. If we have a positive slope coefficient greater than 1, this suggests a strong positive relationship between the input and target variables. A unit increase in x drives a more than 1 unit increase in y. In the second example, a change in x drives only a small change in y, so the slope coefficient is smaller. Likewise, a negative slope coefficient suggests a negative relationship between the input and target. In summary, the linear regression line of best fit can be summarized by a straight line equation. The parameters that define the line are called coefficients, and these help us understand the interaction between input and output variables. One input variable is rarely enough to make good predictions about a target variable. And so with that in mind, we can explore multiple linear regression, which allows us to predict a target variable using multiple independent variables. Suppose we now use 2 explanatory variables to try and explain our target. It becomes a little bit more difficult to visualize our data points and line of best fit, but we can still achieve it, this time using a plane through a 3D field. The plane can be summarized by an equation, this time with one additional parameter. Now x1 and x2 both have their own coefficients, which define how those variables affect the output, y. Again, we still have an element of random error around our plane. Our plane isn't perfect, but it's a good generalization of the relationships between all these points. So in summary, multiple linear regression helps us predict a target variable using more than one input. Alright, so we know that the line of best fit can be summarized with an equation. The equation shows us the optimal line. But what exactly is the optimal line of best fit? Well, generally we try to minimize the size of errors in our predictions. Errors represent the amount by which the target variable is different from the value predicted in our line. Some of our predictions here are too high and some too low, so our errors can be positive or negative. So we have to take that into account when minimizing the total error in the model. And there's a few different metrics that can help us focus on the size of the errors, regardless of their direction. The first three all focused on squaring the error terms to remove those negative values. The other group rely on taking the absolute value of errors. The most common approach minimizes the sum of squared errors, or SSE, and is known as the ordinary least squares method. In terms of choosing between all of these metrics, one common reason is that the squared error metrics tend to be more sensitive to outliers than the absolute ones, simply because we're squaring those large values. So in summary, we have two clear options for minimizing errors. Minimize the squared errors or minimize the absolute errors. And the most common approach is ordinary least squares. Regression coefficients help us understand the interaction between variables. And as we've seen, each independent variable has its own coefficient. So if we look at this in the context of a marketing scenario, where we have both ad spend and product review scores as inputs, we're trying to make predictions about sales, and we can see that this plane summarizes the data points. The equation for the plane is summarized by this equation. Sales equals 2,000, so that's the intercept, plus 1.3a plus 0.11r. So a here is ad spend, and r is the product review scores. So the coefficient of ad spend is 1.3, and we can say that for every unit increase in ad spend, sales will increase by 1.3. Likewise, the coefficient for review scores is 0.11. So we can say that for every unit increase in product review scores, sales will increase by 0.11. So it's still a positive relationship, but the coefficient is smaller. There's various tests we can do to see how reliable and how much we can trust them to make predictions. And so the key point I want you to remember is that p-values help us understand if our coefficients are statistically significant. We'll dive into examples in our regression course, but for now, just remember that the p-values are important. As you'll see, an important part of all machine learning models is that we separate the training and testing processes. Models need to be tested on new data before we allow them to make real-world decisions. So first, we use a set of training data to teach the model what the relationship looks like. Next, we test the model and look at how it performs on a new set of data. If the performance is good, then we can move on to making predictions with real-world data. It's very important that models are tested on data they've never seen before, as well as just being good practice to test things before using them in the real world. The performance on training and testing datasets can also give us clues as to how good the model is. And we'll see this in the next video when we look at the concepts of over and underfitting. Overfitting and underfitting describe how well or how poorly a model fits the training data. We can use performance metrics on the training and testing data to test for these characteristics. An underfit model overgeneralizes the trend, usually because the model is too simple. And we refer to this as a high bias error, where bias is the error created by oversimplification. An overfitting model learns a relationship that is too specific to the training data sample. This is caused by a model generally being too complex, and an overfit model is said to have a high variance error, where variance is the extent to which the model has focused too much on the randomness in this dataset. So somewhere in between we have a good fit of a model, which makes a good generalization of the data point. And we can summarize the two types of errors that we've been talking about, bias and variance, where a simple model has high bias and a complex model has high variance error. And so we're looking for a model somewhere in the middle which gives us a good fit. In the regression folder of the student files, I've included a couple of Excel workbooks that are going to help us walk through the basics of the line of best fit and calculating errors. So on the first tab, line of best fit, we have a simple scenario with years of experience and salary. And I just want you to plot a basic line of best fit. To start with, all we're going to do is plot a basic scatter chart. So I'll highlight the two headers and the remaining data, insert, chart, and I'll choose a scatter chart there. So there we can see each of the data points on a chart with years of experience, our input variable on the x-axis, and salary, our target variable, on the y-axis. Now, at the moment, this doesn't really help us make predictions. So right-click on one of the data points and click Add Trend Line. And so there we see the line of best fit, which Excel has calculated for us. If you go to the Format Trend Line options by right-clicking on the line, you'll see this menu on the right, where we can display the equation on the chart, and we can show this value called r squared. And so this equation defines the position of this line of best fit. We see an intercept here of 25,000, which represents the point at which that line would cross the vertical y-axis. And then we have a coefficient of 9,450 for x. And so that's telling us that for every additional year of experience, we would expect to gain 9,000 in salary. The r squared value is telling us what proportion of the variability in the target variable can be explained using our input. And so in this case, we get a fairly high value of 96%. And that makes sense because the points are fairly tightly centered around this line of best fit. It does a good job generalizing the pattern. I'll leave you to add a more informative title there and to label each of your axes. On the second tab, instead of letting Excel calculate the line of best fit, I've included these two parameters, intercept and slope. Using those, the regression line is calculated. So take a few minutes to have a play with this tab. Change the intercept and change the slope, and see what happens to that line. Take a look also at the errors calculations and the squared error and the sum of squared errors. And this will really help you to understand exactly what's going on when this regression line is calculated. Hopefully you've had a chance to play with those parameters and see how that affects the line that's plotted on your chart. In this video, I want to go through quickly these calculations and how that helps Excel calculates the optimal line of best fit that we see on the next tab. So still on tab 2 here, I've deliberately put the intercept too low. The line this creates is clearly too low to generalize the pattern above. But let's see how that plays through in the calculations. So the regression line is calculated as the intercept plus the slope times the years of experience. That is the regression line equation. As we can see, the line is currently plotted below all of the points, so I would expect all the errors to be negative, and they are. The errors for each observation are calculated as the regression line minus the actual observed value. We square those values to get the squared error, and then sum all of these squared errors to get the total sum of squared errors. And that is the value that we're trying to minimize. Obviously, it would take a lot of effort for us to do that manually. So Excel does it for us and calculates the optimal line. At the moment, it's implemented this via a scatter chart and the trend line that we see. But Excel also has some data analysis packages that allow us to do that regression. If we highlight that input data and then select regression from this list, we can actually construct a more detailed regression analysis, including coefficients and residuals. And we'll cover this in more detail in our regression course. There are defined formulas for the slope and intercept, which we see here, which Excel uses to calculate the optimal line. Now that we have the line of best fit, we're able to make new predictions using new values we haven't observed before. So just scrolling down slightly in the final tab, supposing I have 6.25 years of experience. My line of best fit now gives me a prediction of 84,000 854 as my predicted salary. We can do the same thing with 8.25. And so with our line of best fit, we can easily start to make predictions about new values. Whilst it can sometimes be helpful to bring simple regression analysis into Excel, Python gives us a way to implement models that are faster, more powerful, and can deal with more data. And not only that, but we can then integrate the code with real-world data, real-world applications to provide us with continuous insights. This is one of the notebooks that we'll walk you through in our regression course, where we'll actually go through and write each of the lines of code. For now, I just want us to run through this notebook and see what happens as we run the code. The data and the Python notebook should be in your student files, and if you need instructions on how to load this notebook, I've included a link below. So the first cell, as they're called in our code, is just importing some functionality into Python. Stats models in particular is giving us the functionality to run machine learning models in this notebook. Once we've run that cell, the next step is to load our data, and we're grabbing that from a CSV file and placing it into what's called a data frame. It's basically like a table that you would have in Excel. Once we've imported that, we can see the size of the table by running this shape function. So we can see we've got 63 rows of data and 2 columns. Let's inspect the data to see what it looks like using the head function. So we have 2 columns, one for the number of claims that have been made, and the second column for the amount of payments. So if we look back at the task at the top, we're using the number of claims as our input variable to predict the amount paid, or the payment. Okay, let's try and visualize some of that data. These 4 lines of code plot a scatter plot between the input and the output, add a couple of labels to the axis, and then show that plot. So the scatter plot already gives us a clue that there is a relationship here. We seem to have a couple of outliers in the top right, and the variability in our points seem to be more tightly packed on the left-hand side. Okay, let's fit our linear regression model. The first step is to split our data into inputs and outputs, which we'll call Y insurance and X insurance, and all that does is to split the table in 2. With just a couple of lines of code, we're then able to create an ordinary least squares or linear regression model and fit it to the dataset. We can print the results of this model by running the next cell, and there we see all the coefficients, parameters, and metrics that are going to help us evaluate that model. We see the coefficient for claims is 3.4, meaning that for every additional claim we make, we expect an increase in payments of 3.4. Our R-squared says that our inputs account for about 83% of the variation in our data. We can pull out some of the key variables if we want and print those out explicitly. And finally, using just a few lines of code, we can create a new scatter plot which includes our line of best fit. When we run that, we can now see the line of best fit generalizes those points pretty well. And so as we said before, the benefits of doing this in a notebook or in Python in general is that our models can handle more complexity and more data. These notebooks give us a nice way to lay out code and intersperse it with commentary on the analysis we've done. And if we were going to deploy this code as a real-world project, we could take just the code portions and embed that in a real-world app. Let's take a look at some more advanced regression techniques beyond linear regression. The first one we have here is repeated measure regression, which is where values are sampled repeatedly. This often happens in medicine where a patient may have the same measurement taken at regular intervals. We have polynomial regression, which is used to create smooth, non-linear relationships. The higher the power that x is raised to, the more complex we can make this relationship. Segmented regression acknowledges that the line of best fit may be different for different regions of x. For example, maybe with house prices, beyond a certain size, the relationship of size to price is different. Bayesian regression tries to give us a level of certainty along with our coefficient predictions. Generalized additive models recognize that actually within our data there may be several different underlying patterns that work together to create the overall relationship. So we're effectively able to combine different regression techniques to form one overall average line. Poisson regression allows us to model counts of something, like the number of vehicles that pass a certain point in a given minute. And finally, logistic regression is typically used for classification problems and helps us transform a continuous output variable into this S-shaped curve. So there's a quick insight into the world of regression. We'll cover each of these in a little more detail in our regression analysis course.